NEC Section 220.87 permits the use of demand factors based on historical data when calculating service loads. This is particularly useful when dealing with prototype designs where initial calculations might be overly conservative compared to actual operational loads. The underlying principle is to avoid oversizing electrical equipment, leading to unnecessary costs, while still ensuring sufficient capacity for safe and reliable operation. To accurately apply 220.87, several key factors must be considered. Firstly, it's crucial to have a substantial amount of historical data. This data should represent a typical operating cycle and account for seasonal variations, production schedules, and potential future load increases. The more comprehensive and representative the data, the more reliable the demand factors derived from it will be. Secondly, the historical data must be meticulously analyzed. Identify the maximum demand recorded over a reasonable period, typically a year or more. This involves not only the peak demand, but also the duration and frequency of such peaks. Software tools and data logging equipment can significantly aid in this process. Thirdly, understand the components that contribute to the overall load. Segregate the loads into different categories such as lighting, heating, ventilation, air conditioning, machinery, and other specialized equipment. This detailed breakdown is essential because different types of loads may have different demand characteristics. For example, lighting loads are often continuous, while machinery loads may be intermittent. Fourthly, calculate the demand factor for each load category. The demand factor is the ratio of the maximum demand of a system, or part of a system, to the total connected load of the system or the part of the system under consideration. It essentially represents the percentage of the total connected load that is likely to be in use simultaneously. To determine the demand factor, divide the maximum demand recorded for a load category by the total connected load for that category. For instance, if a group of machines has a total connected load of 100 amps but the maximum demand recorded is only 30 amps, then the demand factor is 0.3 or 30%. Fifthly, apply the calculated demand factors to the connected loads to determine the design load. This involves multiplying the connected load of each category by its corresponding demand factor. The results are then summed to obtain the total design load. For example, if lighting has a connected load of 20 amps and a demand factor of 1.0, the design load for lighting is 20 amps. If machinery has a connected load of 100 amps and a demand factor of 0.3, the design load for machinery is 30 amps. The total design load would be 20 amps plus 30 amps, which equals 50 amps. Sixthly, consider any applicable code requirements and safety margins. While 220.87 allows for demand factors based on historical data, it's crucial to ensure that the resulting design load complies with all relevant electrical codes and standards, such as the National Electrical Code or NEC. Additionally, it's prudent to include a safety margin to account for unforeseen load increases or changes in operating conditions. A common practice is to add a percentage, such as 25%, to the calculated design load to provide a buffer. Seventhly, document the calculations and assumptions. Maintain a detailed record of all calculations, assumptions, and data used to derive the demand factors. This documentation is essential for future reference, troubleshooting, and compliance with regulatory requirements. It also allows for easy review and verification of the calculations by qualified professionals. Eighthly, periodically review and update the demand factors. As operating conditions change, the historical data used to derive the demand factors may become outdated. Therefore, it's essential to periodically review and update the demand factors to ensure they accurately reflect the current load characteristics. This review should be conducted at least annually or whenever there are significant changes in the load profile. Ninthly, consult with a qualified electrical engineer. Applying 220.87 and deriving demand factors based on historical data requires a thorough understanding of electrical engineering principles and practices. It's always advisable to consult with a qualified electrical engineer who can provide expert guidance and ensure that the calculations are accurate and compliant with all applicable codes and standards. Tenthly, the original main distribution panels or MDP was sized in accordance with the NEC. You mentioned that the MDP should be larger, perhaps 1200 amps versus 1000 amps, along with service feeder. You also mentioned that there is a significant amount of historical data to indicate this is not required, as the actual peak load less than 1/3 of the calculated demand load. With this information you may be able to avoid increasing the size of the MDP and service feeder if you have enough historical data to suggest that the actual peak load is significantly less than the calculated demand load. Be sure to follow all applicable codes and standards, and consult with a qualified electrical engineer to ensure that the calculations are accurate and compliant with all applicable codes and standards. 11thly, using historical data to determine demand factors requires careful consideration of several factors. First, verify the accuracy and reliability of the data. Ensure that the data logging equipment is properly calibrated and that the data is free from errors or anomalies. Second, consider the diversity of the loads. If the loads are highly diverse with different operating cycles and peak demand times, then the demand factor will likely be lower than if the loads are all similar and operate simultaneously. Third, account for future load growth. The demand factor should be adjusted to account for any anticipated increases in load due to expansion, new equipment, or changes in operating conditions. Fourth, consider the impact of power factor. Low power factor can increase the current drawn by a load, even if the actual power consumption remains the same. Therefore, it's important to consider the power factor when calculating demand factors. Fifth, ensure that the demand factors are appropriate for the specific application. Demand factors vary depending on the type of facility, the type of loads, and the operating conditions. Therefore, it's important to use demand factors that are specifically tailored to the application. Sixth, consider the impact of harmonics. Harmonics can increase the current drawn by a load and can also cause other problems, such as overheating of equipment. Therefore, it's important to consider the impact of harmonics when calculating demand factors. Seventh, ensure that the demand factors are consistent with the utility's requirements. The utility may have specific requirements for demand factors that must be met. Eighth, consider the impact of voltage variations. Voltage variations can affect the current drawn by a load and can also cause other problems such as equipment malfunction. Therefore, it's important to consider the impact of voltage variations when calculating demand factors. Ninth, ensure that the demand factors are properly documented. The documentation should include the data used to derive the demand factors, the calculations performed, and the assumptions made. 10th, consider the impact of renewable energy sources. Renewable energy sources, such as solar and wind, can affect the demand on the electrical grid. Therefore, it's important to consider the impact of renewable energy sources when calculating demand factors. Applying NEC Section 220.87 using historical data requires a thorough understanding of electrical engineering principles and practices. It's always advisable to consult with a qualified electrical engineer who can provide expert guidance and ensure that the calculations are accurate and compliant with all applicable codes and standards.